Let's take a look at some reductions. So we'll see reduction using a different source of hydrides essentially. So LAH is kind of our go-to source of H minus. So here, if you look at an ester, you can add step number 1, LAH, and you form an RCH2O minus. Now, those H's come from LAH. And then our second step here, that's your acid workup. So that H right there comes from our H3O plus. Right? Remember, sometimes you'll see instead of H3O plus, you might see D3O plus. And then that would just be an OD right there. Or sometimes instead of LAH, you see LAD. So then it would be a CD2 for deuterium. All right. Now, if you look at the reaction mechanism down here below, it's fairly straightforward. You have H minus attacking your carbon here. And so there's an H that's hanging out right there. Lone pair swinging down, kicking off your alkoxide, which is probably complex with AlH3. And remember, the reaction doesn't stop here. It continues on to form, in this case, the alkoxide. Now, the other reagent that I want to show you here to remind you of is this. So here we can take our ester, something like that. We can add one of two reagents. So LiAlTBuO3H. Remember that? Or we can add diabal H. Right? In that case, these both take the reaction to form the aldehyde. So just make a note here that the reaction stops here. Okay? So again, kind of looking down below, we kind of see that, right? So SOCO2 makes an acid chloride, except here above we started with an ester. Down here below, we're converting that to an acid chloride. That's the context in which we saw that lithium tri-T-butoxy aluminum hydride from previous chapters. But in both cases, it takes us to our aldehyde. Now, reduction 2 amines can also occur. So we can take our amides, our nitriles, and also azides down here below, and do a reduction with LAH and H2O. And just like before, that comes from your LAH, and this comes from the H2O. Well, let's take a look here at your acid derivatives and organometallic reagents. Now, this is a reaction we've actually seen before. We saw this in first semester, but it's been a while. So if you have an ester here, for example, and add your R-MgBr, remember that R-MgBr is reacting in essence like an R minus. So it's going to swing around and grab that carbon, and then we're going to plop those electrons up to the top there on that oxygen. So then that's going to give us this. That is your tetrahedral intermediate. Then those electrons are going to come back down, and then we're going to kick off O minus there. So you have, in that case, methoxide. But the reaction doesn't stop here. So we're going to have an R minus swinging around and adding a second time. Right, that's going to give us this. And then our step 2, so this is really our step number 1. And our step 2 is simply your acid workup, where you're coming over here and you're gaining the H, again, probably from H3O plus. So you'd go get hydrochloric acid or something along those lines. Other note here too is that you also get, because this was kicked off as CH3O minus, you technically also get CH3OH. So some textbooks are going to want that to be written out. Now the mechanism's similar for acid chloride, so I'll let you take a look at that, and I think you'll be able to work your way through it. Now for nitriles, reaction is very similar. So a nucleophile attacks this carbon. Right? That would in essence put a negative charge down here at the end. So The other way that some books will write this is simply that. Right? Hydrolysis of that still gives us this fellow over there, and that is an imine. Right? So imine hydrolysis would occur from that mechanism that we saw back in chapter, I believe it was chapter 18. Right? So take a look back at chapter 18 if you need to review that mechanism.